Good afternoon, class. Am I audible? Good afternoon, class. Am I audible? Okay, let us start with the today's class. Uh, so today we are going to learn about the Bayes code normal form. So let us revise the previous lectures. So in the previous lectures, we have studied the concept of functional dependency. So functional dependency, it means that the value of some another attribute is implied or is dependent on some another attribute. So here, given a set of sorry, this is a closure. So here, the functional dependency alpha holds on beta. So this functional dependency can be part of R if and only if for any legal relations. Legal relations, it means that those which relation satisfies all the constraints of the real world, those relations are called as a legal relation. For example, student can enroll for a single branch. If that constraint is followed by my relation, then that relation becomes a legal relation. So, if and only if any legal relation R of R, whenever any two tuples T1 and T2 of R agree on the attribute alpha, they also agree on the attribute beta. So it means if there are two tuples T1 and T2 for whom alpha attribute have the same value, then for the beta also these two tuples must have the same value. Then we can say that beta is functionally dependent on the alpha. So this dependency, our complete chapter is based on the same functional dependency. So here this is example is given where this is my A attribute, the first attribute, and second attribute is a beta attribute. So in this, the beta attribute is not dependent on the alpha because one for the one we are having 4 value and for the one we are having 5 also value. So it means beta constraint doesn't hold. And because of this, we may say that beta or this second attribute is not dependent on the first attribute. But on the second attribute, first attribute can be dependent. This dependency we can show. So, uh, functional dependency we have seen. Next, we have studied the second normal form. Second normal form says that there should not be any partial key dependency. Partial key dependency, it means that whatever my key attributes are there, remaining attributes should be dependent on the key attribute. If these attributes are dependent on the part of the key, then that is called as a partial key dependency, which is not allowed in the second normal form. So we can say any relation is in the second normal form if and only if it should be in the first normal form, that all the domains should be atomic. And second condition, that these attributes should be fully dependent on the primary key of the relation. Or instead of primary key, we may say the candidate key. So there can be multiple candidate keys can be there. If these are dependent on these attributes, that also works on the second normal form. So but here the partial key dependency should not be there. The attribute should not be dependent on the part of the primary key or part of the key. These should be fully dependent on the key attribute. That was the second normal form. Then next we have seen the uses of functional dependencies where we are going for the legal relations where satisfaction of F gives us to calculate how we can decompose them. Next we have seen the functional dependency, trivial functional dependency. So here if the left hand side, the beta attribute is a subset of alpha, then that dependency is called as a trivial dependency. So trivial dependency is satisfied by all the instances of a relation. So here this trivial dependency we are going to use in the next calculation of the closure. Next, the closure. Closure is actually the part which need to be covered after the fourth normal form. Okay. So here a simple one slide is introduced just to know the concept of closure. So closure, it means that there can be some functional dependencies which are implied by the given set. Okay, so it means that here if I'm having the functional dependency alpha A holds on B holds C, and it implies that A holds C. So this type of functional dependencies are called as implied. It means which are not given in the set but are available or can be logically implied. So set of such implied functional dependencies is called as a closure of set of functional dependencies. So any doubt in the previous lectures? So any doubt in the previous lecture? Okay, let us start with the today's lecture. So today we are going to learn about the bias code normal form. So this is a special form, normal form designed that here the main thing is that whatever the normal forms are given, these are given with the first normal form, second, third or fourth or fifth, etc. So bias code normal form is with respect to the closure. Okay, so let us see about this. A relational schema R is in the BCNF with respect to a set of F functional dependencies. If for all functional dependencies in F closure, okay, of the form alpha gives beta, where alpha and beta are subset of R, at least one of the things hold, that is here alpha holds on beta, that is a trivial functional dependency is there, that is beta is a subset of alpha, and second point is that alpha is a super key of R. So okay, here the dependency is based on the super key. So this allows us to have a, it means a somewhat relaxation as compared to the previous normal forms. So in the previous normal forms, always a key attribute is taken as a primary key, that is a candidate key is always chosen. But here whenever we are talking about the bias code normal form, this mainly uses a super key. It means we can have a set of elements in order to have a show to the dependency. So, okay, consider this schema: ID, name, salary, department name, building name, budget. So, this is not in BCN because on the department name, building and budget is dependent, and department name is not a super key here, but we can go for ID and department name. And on this, if we show that these two are dependent, then we say that this relation is in the BCN. So, but here building and budget, these are not dependent on the ID. So we cannot include the ID attribute here. The point here is that here, whatever my alpha is there, that should be a super key. It need not to be minimum, but it should be a super key. Next, decomposing the schema into the BCNF. Suppose we have a schema R, that is a set of attributes and non-trivial dependency. Non-trivial, it means that alpha is not, beta is not a subset of alpha, causes a violation of BCNF. So we wanted to decompose this relation. Then we will decompose R into two subparts. That is, we will combine alpha and beta into union with the first relation, and second relation will be the with this. Okay. So right now let us take an example of this. Okay. This is my and let us say alpha. Okay, what is my alpha and what is my beta that we wanted to check. Still people are joining. So here, as per our example, we will take these two as alpha and beta because this functional dependency doesn't let us to satisfy the condition of BCNF. So we wanted to decompose this relation alpha and beta, and we should have a decomposition of relation as per these two rules. So, okay, these two rules are there. So the first relation R1 will be decomposition. So this is my complete R. So this can be shown or considered as R of R. So okay, R it means the name of the relation. This R, capital R, it means this is a set of complete attributes, complete set of attributes of relation. And alpha it means department name, beta it means two attributes building and budget, and we are having the dependency of alpha holds on beta. So here the uh, super key super key dependency is not available. That's why we wanted to decompose this relation. So we will remove this. So the first relation will be alpha union beta. So alpha department name, alpha department name, beta building and budget. These two will be in the first part, and in the remaining, in the second relation, we will have attributes. So this R, so it means this will be my complete set. This will be my R minus beta, beta minus alpha. Okay, as these two are non-trivial, it means that beta minus alpha will not give us anything, and because of this, so this is my complete relation or equation. So within that, let us calculate the inner bracket. So this bracket, building minus budget and deducting the department name. So this will not deduct anything and will give us the R2 relation, which same as it is. These two, building and budget, will remain as it is, as none of the attribute get deducted. And after this deduction, remaining attributes, as right now, let us remove this bracket. So now we wanted to remove building and budget. So building and budget will be get removed, and hence we will have this relation as our second relation. Okay, building budget and department name as our first relation, and second relation will be ID name, salary, and department name. Now let me know whether there is a dependency of remaining attributes on the super key exists for this, whether there is any partial key dependency, or whether there is any uh, dependency not on the other than the super key attributes exist or not. So you can send the reply in the chat window also. Is there any existence dependency completely on the any super key? Let us take attribute by attribute. Building and budget both are dependent on the department name, and hence we can say that department name can be a super key in this first relation. Okay, and in the second relation, name is dependent on the ID, salary is also dependent on the ID, department name, that instructor's department name is also dependent on the ID, and hence this is also a dependency on primary key or super key exists. And we say that as building and budget got removed from the R2, we do not have any partial key dependency or dependency on the non-key attributes. And hence we can say that the given relation or given decomposition R1 and R2 is in the BCNF format. So clear with this? May I repeat by taking some another example? May I explain this with another example? Okay. Right now, assume that you have understood, and we wanted to move to the next point. Okay. Yes, I got the reply, few of them. So let us move to the next point. So next, BCNF and dependency preservation. So here we wanted to preserve, always we want the lossless decomposition, and we should be able to preserve the dependencies also. So for there, we are covering this point. So constraints, including functional dependencies, are costly to check in practice unless they pertain to only one relation. So here the first point says that whatever our joining constraints are there, we can check for the data, but checking the functional dependency exists or not, that should be checked. It means before the decomposition, if we are having the three functional dependencies that A gives B, B gives C, or BC gives D, etc. Any kind of can be there. Consider there are three sets. And after the dividation, checking whether these functional dependencies are still preserved, that may be a costly procedure. It is sufficient to test only those dependencies on each individual relation of decomposition in order to ensure all functional dependencies hold. Then that decomposition is dependency preservation. The second point says that after the decomposition, okay, if we are able to calculate these or preserve these functional dependencies after calculating or checking the functional dependency between the all decomposed relation, then that is also individual checking for the individual functional dependency, that can be also a solution for that. And because it is not always possible to achieve both BC and BCNF, BCNF and dependency preservation, that is a third normal form. Okay, so BCNF is stronger than the third normal form. So here we cannot check whether dependency preservation exists or not. But in the third, this is a, we can, if we are not able to preserve the dating relation into BCNF, then we can move to the third normal form also. So let us see the third normal form. Normal form, here a relation schema R is in the third normal form if for all alpha gives beta in F closure, okay, at least one of the following holds. So here we are talking about the trivial functional dependency and transitive functional dependency. So the first condition is that alpha gives beta is a trivial functional dependency. Yes, that is a left hand side is a superset of right hand side. Then alpha is a super key of R, that is a dependency on the key. And each attribute A in alpha is contained in the candidate key for R. Okay, so here this is the main point given in here, that beta minus alpha, this set of attributes is contained in the candidate key for R. So here we are talking about those relation, this relation where we will say that this relation is weaker, but here the remaining attribute should be a candidate key. If a relation is in BCNF, it is in 3NF also. That is a, since BCNF is one of the first two conditions above must hold, that is these two conditions are also applicable for the BCNF. The third condition is a minimum realization to BCNF to ensure dependency preservation. So here, whatever this third condition is there, that is relaxed in the BCNF. And so, and because of this, those relations which are in BCNF are always is in third NF, but third NF relations may not be in the BCNF. Okay, now let us go to the goals of normalization. Let R be a relational schema with a set F of functional dependencies. Decide whether a relation schema R is in good form. So for this purpose, in the case that relational schema R is not in good form, decompose it into set of relational schemas R1, R2, Rn such that each relation schema is in good form. The decomposition is a lossless join decomposition. Preferably, decomposition should be dependency preservation. So here, decomposition should also preserve the data as well as preserve the dependencies. How good is the BCNF? Any doubt in this? Any doubt in this? Okay. So there are database schemas in BCNF that do not seem to be sufficiently normalized. Consider a relation. Instructor info, that is this instructor is having a child, and for communicating with this child we are having a phone number, where instructor can have more than one phone number and can have multiple child also. So for this purpose, consider we created a table which will store ID of the instructor. Consider that there are two phone numbers and that instructor is having two child. So here, whatever the phone number we are writing, that is applicable to the both childs. And if there are four phone numbers are there, then we may have we will store this information here. Consider this is the instructor who is having a child David, and for the David we are giving this phone number as that this can be a phone number through his attribute. Okay. Next, for the David, second phone number also available. That this with this phone number also we can communicate. And as this instructor is having another child, William. So for the William also, these two phone numbers, this first one and second one, both are applicable. So here, don't you think that this is a repetition of the data is there? So here child name is also dependent on the ID because this child belongs to the this instructor. Phone number belongs to this instructor. But here this ID, that this attribute, consider this as alpha and this is beta. Do you think that this relation can be in BCNF? Whether this relation is in the BCNF? Or whether the functional dependency is by this relation. Okay, there are non-trivial functional dependencies. It means here, even though this relation is in the BCNF, that is also also dependent on the ID. This phone number is also belonging to ID, and hence this is also dependent on the ID. But here the main thing is that here we cannot use the key attributes, or we cannot say that this is a directly any functional dependency because we are having the multiple values, and hence this relation is not in the BCNF. Okay, so there are non-trivial functional dependencies and therefore relation is in the BCNF. Insertion anomalies, we may, if we add this phone number to only one child and another phone number with the another child, then we can say that right now this relation is in the BCNF, that trivial functional dependency exists for this. But this is not a correct way. For this purpose, we are having the another normal form, that is the fourth normal form. Okay. So for elaborating this, we may have this as separate table and this as a separate table. And by this, we know that BCNF is unable to store such information. And that's why we are moving towards the higher normal form, that is a 4NF. And 4NF is used for the multi-value dependencies, that multiple, for a single value, there are multiple value exist. Let us see the functional dependency theory. So functional dependency theory, we now consider the formal theory that tells us which functional dependencies are implied logically by a given set of functional dependencies. Then we develop algorithm to generate lossless decomposition into BCNF and 3NF. And we develop the algorithm to test if decomposition is dependency preserving or lossless decomposition is there. So for that purpose, we need a closure of a set of functional dependencies. Given a set of functional dependencies, there are certain other functional dependencies that are logically implied by F, that A gives beta, A holds on B, B holds on C, then we can infer that A holds on C. The set of all functional dependencies logically implied by F is the closure of F. We denote this by F plus. Now let us see the procedure for this. So for this, we study some rules, that is inference rules. So for this, these rules are called as Armstrong axioms. So there are three rules, that reflexivity, augmentation and transitivity. Okay, let us see the reflexivity. Reflexivity says that the alpha holds on beta. This rule is true whenever there is a beta is a subset of alpha. Okay, just like if I take ID and name here, then name is dependent on the ID and name. So it means name is a subset of ID and name. So in this way, this first functional dependency there, reflexivity, which reflects its own on the left hand side. Next rule is augmentation rule. Augmentation rule says that if we are having the existing functional dependency, alpha holds on beta, then we can add some another attribute gamma on the both sides. Okay, so gamma alpha and gamma beta. This functional dependency also we can show, or this is also implied functional dependency. And next one is a transitivity, which we have studied previously also. So if alpha gives beta or alpha holds on beta and beta holds on gamma, then it implies that alpha holds on gamma also. So these rules are called as Armstrong axioms, which are used for calculating the closure of F, closure of F, and on this the uh, decomposition of relation is based. So these rules are sound, that is generally only functional dependencies that are actually whole, and these are complete, that these rules will give us the complete all set of the all possibility. There is no any functional dependency which can be implied but not included by these rules. By applying these rules, we can go for calculating the F closure properly. So for this, let us consider an example. So here, right now, we are having the R, relation R, which is having a A, B, C, G, H, I, these attributes as a part of R, and we are having the functional dependency A holds on B, A holds on C, CG holds on H, CG holds on I, and B holds on H. So here, let us calculate. First, include all these functional dependencies, and then by applying the first rule, okay, let us apply the first rule, that is the reflexivity. So reflexivity here, every attribute on this side is not available, only A is missing. Okay, B, C, G is also missing. So G, H and I. So except A and G, all the attributes are included on the right hand side. And that's why here we should go for adding the G on the right side. So reflexivity rule says that here we are having G on the right hand side. Okay, let us go as per the explanation given in the slide. So we can have this functional dependency implied because alpha holds on B and B holds on H. So we can imply that A holds on H. Okay. Then next, A holds on C. So if consider, we replace C by H. Okay. So here by augmenting, here A gives C is there. So G we will add to the both sides. AG gives CG, and then by transitivity we know that CG gives I. Then we can see that this CG, that AG gives CG and CG gives I, we can see that AG gives I. Okay, so here we applied the augmentation rule, and here one more rule is there, that is implied. Here CG gives CHI. So how we can calculate this? By augmenting CG gives I to infer CG gives CGI. Yes, because here reflexivity rule got applied. Whatever on this side, always available on this side. Now by augmentation of CG gives H, so we can reply that by this CG we can replace the H, and hence CG gives HR. Okay, and then we calculate this rule. So here these will be the members of F closure. Clear with this? Clear with this? Okay. Now let us see what is the procedure for calculating the F closure. So F closure is nothing but applying these rules repeatedly unless and until our F closure doesn't change. Okay, so here rule is that to compute the closure of set of functional dependencies F, so F plus gives F. So initially whatever F closure is there, that will be equivalent to the given set F. So we will repeat this until each functional dependency F in the F plus. It means whatever 5 to 6 dependencies are there, on each of the functional dependency we apply these rules. So first we apply reflexivity, that is subset rule, and augmentation rule on F, and whatever resulting functional dependencies are there, that will be added to the F closure. And for each pair of functional dependencies in F1 and F2 in F plus, if F1 and F2 can be combined using transitivity, then we add these resulting functional dependencies to F plus. And this we will repetition until F plus doesn't change any further. Okay. So here we are applying these rules unless and until F plus doesn't change. Please go through this procedure. So there are other ways also to calculate this functional dependency. As we proceed with the chapter, we will see how to decompose the relation as well as how to calculate the F closure. So here, there whatever Armstrong axioms are there, these are it means modified to add some rules. So here there are three rules added to the given rule. Uh, First one is union, next one is a decomposition, and last one is the pseudo transitivity. So let us see what is mean by each of the rules. So if consider we are having alpha holds on beta and alpha holds on gamma, then we can go for union of beta and gamma. That is, whatever left hand side is there, we can perform the union. Whenever there is a, sorry, right hand side we can combine whenever there is a left hand side equal for these two. Okay, so here also alpha is there and here also alpha is there. It means that we can go for union of beta and gamma. So this rule is called as a union rule. Okay. Next, if consider we are having, we can go for dividation also. So that is a decomposition. If we are having beta gives gamma, then we can say that alpha holds on beta and alpha holds on gamma also. So this rule, decomposition rule is there. And last one rule says that pseudo transitivity. If we are having alpha holds on beta, okay, and beta gamma holds on delta, sorry, this is yes, delta, then we can say that instead of beta we can use the alpha and then say that alpha gamma holds on delta. Okay, so make equivalence of this side and this side. We add alpha to the both sides on this. So it means here, in order to make the equivalence, we add gamma on the both sides. So that's why this rule is called as a pseudo transitivity. And these rules can be taken as a part from the Armstrong axioms. And hence, by using this also, we can calculate the functional dependency. Any problem in this? So here, up to now, we were studying about the closure of functional dependencies, but there can be closure of attribute set also. That is, if I'm having alpha, beta as attributes, then how we can calculate the closure for the same. Okay. So here also we apply almost the same rules, but the problem is that we cannot apply the Armstrong axioms directly, etc. What your left hand side is there, that we are not going to change. Okay, so it means if I'm choosing the alpha as a set initially, let it be set or set of attributes, that closure will be different from the any other set. It means if there are certain attributes into my relation, then there can be a closure of every attribute. Okay, so given a set of attributes A, define the closure of A under F denoted by alpha plus as the set of attributes that are functionally determined by under F. Okay, that we wanted to calculate. So algorithm is that, so while changes to result for each beta given in gamma in F the beginning, so beta will be, if beta is a subset of result, then we will add this with the result. It's okay. Initially, this algorithm seems complex, so let us apply this on some here. Okay, it is easy to copy or apply the attribute closure on this. Okay, yes, here the same example is taken. So okay, here we are having alpha A gives B, A gives C, etc. Now consider we wanted to calculate closure for the AG plus. Okay, so initially result will be equal to AG by applying the reflexibility that each the same elements can be a part of this. So now here by this next is that if for each beta gives gamma in F, do and begin. If there is a whatever result is there, if this contains beta is a subset of that, then we will add the gamma to the result. Okay, so by applying the this rule, we know that B is dependent on the A, and hence on the A, C is also dependent. Okay, so it means that whatever A is there on A, we are having two functional dependencies, one B and one C. So that will be added to this result by using the previous algorithm that A gives C and A gives B. So that functional dependency will be added here by applying the second rule. Now, here let us now which are the attributes remaining? A, B, C, G, these are the over. Now remaining H and I. So for the H and I, we don't have any dependency which is on the left hand side. So H and I are available on the right hand side only. So if these are available on the right hand side, let us check which is there on the left hand side, CG. Now this CG is a part of this explanation. So now CG gives HI. This is dependent. So this is my beta and this is my gamma. So gamma again will be added to the given result. And hence H will be added and similarly I will be added. Now this complete relation is a part of this AG plus closure or attribute set, and hence we may say that this is a candidate key. Okay, so candidate key it means that here if whatever the attribute closure is there, if this is giving the same relation as the R, then we may say that this is a candidate key. But here the main thing is that AG will be, is it a super key or is it a candidate key? That things becomes mean. So if AG gives R, then AG plus we can say that this closure is giving the R, then we can say that that is a super key. And if any subset of AG is super key, let us check. So whether A closure can give R, if so, then we can say that A is a super key. Or if G also gives us the R, then we can say that G is also a super key. But there is no indication that G is dependent on the A, and that's why we cannot come to this conclusion that A gives R and G gives R also. We cannot make this conclusion because there is no any dependency for G available for C or B or A, etc. And that's why we may say that neither A neither G is a super key, only AG is a super key. So clear with this? Uh, which rule you wanted to repeat me? Pseudo transitivity. Tejaswini? Okay, pseudo transitivity. So here, let us take an example that here I'm having AC and CG in this way. Okay, forget about the remaining rules. I'm having AC equivalent to A gives C and CG gives H. Okay, then what I will do? I will add G on the both sides. Okay, now AG gives CG and CG gives HI. Then I will make the conclusion that AG gives me H. Okay, that is a pseudo transitivity. Normal transitivity is that whatever the right hand side is there, that is equivalent to the side. If so, we may make the conclusion that for A, H is dependent. That is a normal transitivity is there. Pseudo transitivity it means that here in order to make left hand side So here CG is there, here CG is there. But CG is not part of this left hand, right hand side. For this purpose, we add G attribute here and G attribute on this side also. Now we are having right hand side and left hand side equal. Then we make the conclusion that AG gives H. Done with this? I will show you the rule. So here rule is that alpha gives beta holds and beta gamma. Okay, gamma beta holds on delta. So then here whatever gamma attribute is there, here only beta is available, gamma is not available. Then gamma will be available. We will add on the left hand side and right hand side, and hence alpha gamma will give us the delta. Okay, okay. It's okay. We will stop here now. Is anybody else is having any doubt in today's class? So today we covered closure, algorithm, and Armstrong axioms. So in the next lecture, we will solve few of the examples which are asked in the GATE examination on the normalization. That how to calculate the F closure and how to check whether given set of element is a super key or not. That is a closure of attributes. Okay.